So polymers are large molecules made up of repeating units called monomers. If it's only one type of monomer, that's called a homopolymer, so it's just one thing repeating over and over again. If you have two monomers, they can come in a couple different ways. Random, so the second monomer comes in randomly, random copolymer, called copolymers now. A block copolymer means the two monomers are getting in groups, so blocks, or they can be an alternating copolymer, AB, 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 all right, every other one. Biomolecules, DNA, RNA, are made up of, are large molecules made up of repeating units, so these are obviously really important for life. So understanding kind of polymer synthesis and these kind of things, how large molecules work is a little different than we're used to in organic chemistry. We do small molecule stuff, right? So it's kind of a different way of thinking about organic chemistry, these large molecules. Polymer synthesis comes in two ways: addition reaction and condensation reactions. Condensation reactions are losses of water. So those are, we'll talk a little bit more about those in the last unit. The other type are addition reactions. They can come in three ways: radical, cationic, and anionic. Just like it sounds, radical, of course, is going to use our three steps: initiation, propagation, termination. So it's really neat. I always think of these as like a spark that starts the fire, right? This one little, all we need is one radical to make this polymerization just go, right? So you need one initiator that starts the process, right? And that creates that radical, which then, right, initiates and creates a new radical. And notice we can by thinking about resonance, we know where this new radical will be at because this is a more stabilized radical, which then reacts with another monomer unit, propagating, right? Propagating to make a new radical, and that keeps reacting with how much starting material you have, and then you get termination. Eventually, you add in something to either stop it, or you run out of starting material, and you get your polymer. The way these are drawn is kind of different too. You have these like kind of brackets to show you. It's trying to show you what is the repeating unit, like what is the repeating unit. So if you look at this, the repeating unit, see the brackets there, and if you know it's a radical addition, you can essentially say, well, there must have been a pi bond right here. So you'll see this a couple different ways in some of your problems you work on, and it'll ask you, well, what was the unit that was actually from? Right. So kind of where those brackets are, you add a pi bond between there, and that's how you know that's where the actual starting material monomer was. Okay. So beyond radical polymerizations, you can also do cationic or anionic. And it's just like it sounds. So a cationic would be like acidic conditions, right? Cations. So you use acid to initiate the polymerization. Again, by knowing stuff about mechanisms and understanding radical stability or carbocation stability or carbanion stability, we know where the carbocation is going to go, right? More substituted spot because of hyperconjugation in this case. Pi bond is going to react again, and you're going to keep on going. And again, notice eventually you have to have a termination. You add in some sort of nucleophile, right, to stop the cation from forming, right? Or you just keep reacting until you're done. Again, notice the brackets, and notice where the pi bond would be at, right? It'd be right there. Right? So you kind of start recognizing when you see these polymers drawn, can you recognize where the monomer is at within those brackets? So this last one I want to show you, I'm actually going to run to the lab. And we actually did this reaction in lab yesterday, the advanced folks, is this anionic polymerization. So we actually use this called sec-butyllithium, right? So this is an anion, right? Lithium carbon. So it's really, you could draw it as this. Right? You had to be very careful with this stuff. This stuff lights on fire in the air. So be careful with this stuff. So it reacts there. Makes a carbanion, right? So it's like the initiation step. So it's reacting with styrene. And what did we just make? So we made a carbanion. Charge there. Our lithium reacted there, so make sure I do this right. All right? Didn't lose any carbons. Once we have this carbanion, now it's going to look for another monomer, and it's going to react again. And it's going to keep reacting and have that anion until we add in this case, I added in some methanol and actually stopped the reaction. It gets the same type of polymer as up here as the radical, right? But maybe perhaps some, different conditions have different benefits, controls. So it gets to this polystyrene as well, and it can have some different benefits, whether or not you use radical or anionic conditions. These can be done maybe. This had to be much more of an inert atmosphere. We had to do these reactions under nitrogen. Had to be really careful. Had reagents that are pretty reactive. This you could do more in the bench top, perhaps, but maybe sometimes radical polymerizations are harder to control. And so one of the things people talk about in polymer chemistry a lot is not only do you want to make a polymer, you want to make very similar polymers, right? So you can make a polymer that has 100 monomers. You can make a polymer that has 1,000 monomers. You can make a polymer that has 10 monomers. It's not about yield, it's about precision a lot of times, right? If I want to make a polymer, I want all my polymers to have 100 monomers. I don't want, a mixture of those things, right? Because again, if you think about these big molecules, a polymer that has 1,000 monomers will probably have very different physical properties than a polymer that has 10 monomers. Another way to think of it, you know about RNA and DNA, right? Long chain RNAs, right, probably do something different, right? They translate different proteins than a shorter sequence would, right? So you want to be very precise, right? Just like in DNA, you want to have exactly, right, or RNA, you want exactly that strand to be exactly the way it should be. When you do polymerizations, you want precision. You want to have a polymer that is very much, they call this the, blanking, but they want it to be very similar, right? So if you want 1,000, you want 1,000 monomers in there.